15.2 Simplifying Radicals. So in this video, we're going to continue to simplify radicals, and I'm going to add some variable with it. So last time, in the last video, we did a lot of these crazy problem. I want to pick an easy one. Okay. Oh, you know what? Let me pick the cube one. All right. Let me pick this cube one. So we end up looking for three of the same number to go outside. So let me just kind of copy this whole thing down again, and let me kind of rewrite this slightly different. Okay, let me just go to a different page. How about that? Another way of doing this, which is what I like to call a shortcut, but it's really not a shortcut. So if I just simply write down all these twos together, basically inside my cube root, this 192 is made out of 2 to the 1, 2, 3, 4, 5, 6 power times by 3. Okay, so we basically broke down the 2 to the 6 power into two different groups of twos that each one has 3 of them in there. So that's actually the same thing as saying 2 to the third power times 2 to the third power. So this is actually thinking about product rules from the exponents backwards. Okay, so now, okay, this is just me trying to explain to you 2 to the 6, looking at the two groups of threes with three of them in each group. Okay, because cube and cube root kind of cancel each other out. That's why 1, 2 comes out. Cube and cube root canceled out. This 2 will go outside, become 4. Now, another way of looking at this is basically thinking about this exponent in the inside and the roots on the outside. Because you kind of already see there are two groups of 2's with 3 of them in each group. So that's basically saying if I would take the exponent in the inside divided by the roots, okay, that will actually tell me 6 divided by 3. That will tell me there's going to be 2 2's that will go on the outside. Okay, because 6 divided by 3 is exactly 2, remaining 0. So the remainder here, when I take my exponent divided by the roots, tells me how many 2's is going to stay in the inside. Okay, this is a very interesting technique when it comes to variable, because here when I have a square root of 32 times x to the 7 power, the 32 part I can break it down using prime numbers. Okay, if I use a 2, that will be 16. 2 going to 16 8 times, 2 going to 8 4 times, 2 going to 4 2 times, 2 going to 2 exactly 1 time. So basically the 32 is made out of 5, okay, 5 different 2's. But since I'm dealing with the square roots, I only need to take 2 of them to the outside at a time. So these 2 go outside as one of them. These 2 will go outside as another 2. And this 2 don't have nobody to go outside with, so that got to stay in the inside. Okay? Now, so when it comes to the exponent, I can take my exponent divided by the roots. This is a square root, so that becomes 7 divided by 2, which we know is 3 remaining 1. So that tells you there are going to be 3 x's goes out. So that will be 3 x's go out. That will be x times x times x, which is same thing as saying x to the third power. And one of them stays in. This remainder tells you how many x's stays in the inside, which is one of them. And that's my answer. 4x to the third times square root of 2x. Okay, that's how we actually simplify this. Okay, so if I break it down completely, it should look something like this. 32 is made out of 2 times 2 times 2 times 2 times 2. 5 of them, right? Times x to the 7 is 1, 2, 3, 4, 5, 6, 7. So I'm looking for two of the same thing to go outside. So these two go outside as one of them. These two go outside as another one. These two x's go outside as one of them. These two go outside as another one. These two go outside as another one. So I actually have this x to the third is really x times x times x, which is x to the third. Okay, so that's me doing this problem without writing all the stuff out. Because if you keep on doing this, eventually students just kind of get scared of, oh man, this is a lot of stuff going on here. There is. I'm just trying to explain to you in a simpler fashion. So we just kind of trying to find two of the same thing to go outside as one. Okay. When it comes to a lot of exponents, we just use a little kind of shortcut to see how many is supposed to go out, how many stays in. Alrighty. Now this is an interesting problem because this problem I can actually split them up into the division. Like we mentioned before, we can split them up into two parts. And so if you're quick with this, okay, I'm going to write a couple steps here. Initially, it will look something like this once we split them. But if you kind of think about it, though, square root of 16 is going to be 4, right? Here, behind the 16, there are 12 y's being multiplied together. So if I will take the exponent divided by the roots, that will be 12 divided by 2, which is exactly 6, remaining 0. So that tells me 6y goes out and no y stays in. So 6y goes out is y times y times y times itself 6 times, which is y to the 6th power. 35. Think about 35. Break it down by prime number. 35 is only 5 times 7. So there's only 1 5 and 1 7. So nobody can go outside because I don't have two of the same number. So that means my 35 stays inside the square root. All right. The x is right behind the 35. There are 13 of those. So if I take 13 divided by the roots, 2, that will give me 2 going to 13 6 times, remaining 1. So that tells me there are 6 x's goes out, which is x times itself 6 different times, which is x to the 6. And one of them stays in. So my answer, x to the 6 times square root of 35x over, whole thing over 4y to the 6th power. Okay. Now this is a cube root. So I don't know if you remember that 27 is a perfect cube number, which is 3 to the 3rd power. So cube root of 27 should be 3. But let me go ahead and split them up. And let's see who goes out, who stays inside. All right, so cube root of 27 should be a 3 because 27 is 3 to the 3rd power. And cube root cancels out. That will make my 3 goes out. All right, 15. There are 15 y's inside my cube root here. If I take that divided by the roots, 15 divided by 3 is exactly 5, remaining 0. So 5y goes out. None of them stays in. So that means there's no more radical. I keep on forgetting to mention that from time to time. So when everybody goes outside, then there's no more cube root. Okay? I think you can literally do the exact same way as I do, and at the very end, add the cube root back onto it. No, cannot do that. The whole point is to see who goes out, who stays in. Okay, the 3 and the y to the 5th are the one came out. All right, 13 is a prime number, so that cannot be broken down. So that means this single 13 got to stay inside the cube root. All right, x to the 13th power. So let's see, 13 divided by 3. So I'm basically trying to see how many groups of x's, 3 x's together, I can actually make, which 3 going to 13 is 4 times, remaining 1. So there are 4 x's will go out, okay, because there are 4 different groups of x times x times x. So all 3 of them goes out as one of them. So it will end up to be 4 of those goes out. and one of them stays inside. There you go. That's my answer. All right. So in this lecture video, we added a variable, okay, behind our numerical numbers inside the radicals, and showing you a little shortcut to how to handle to how we can quickly handle the variable to determine how many goes out, how many stays in. So I call it a shortcut. It's really not a shortcut. It's just something I have not introduced yet until other sections of this module. All right, that will conclude this lecture video. Thank you for watching.